Hi, everyone. My name is Yikang Xu. I'm here to talk about the lessons we've learned from studying about 10,000 SSD-related failures over 3 years at Alibaba's cloud service. This is a joint work with researchers from Ohio State and Iowa State universities. And the first author of the study is not able to come to this conference, so I'm here to present the work in his place. So flash-based SSDs offers lower latency, higher throughput, and lower power usage at idle time, and is generally considered more reliable than hard drives. So they are increasingly being used in cloud environments. However, they are complicated. For example, SSDs has lower acceptable temperature range than hard drives. And although they use less power at idle, when they're busy, they can use lots of power and generate lots of heat. There has been a number of previous studies about SSD reliability. They mostly focus on the SSD internals and their failure rate and their raw bit error rate and the uncorrectable bit error rate and the impact from FTLs. In our study, we take a holistic view. We look at both the SSD errors and the system errors, failures around the SSDs, and try to establish a relationship between these two. In our study, we focus on failures that we call are reported as SSD-related by our per-node monitoring daemons. Then combined with smart logs, node and device logs, and repair steps and the repair results, we arrive some perspectives from system and administrative point of view. I'll first give an overview of our cloud architecture. This is a very high-level architecture of our cloud service, focused on the hardware part. So it shows 3 main types, node types. They all use SSDs as their system drive. The one on the left has 1 additional SSDs they use for local storage. This is our main compute node. It has very powerful CPUs and maybe GPUs. The one on the left has 2 SSDs, and 12 or 36 hard drives. This is our main high-density HDD storage nodes. The 2 SSDs are used for journal to buffer incoming writes or for storage for hot data. The one in the middle has 12 or 18 SSDs. This is our main OSSD storage node. Not shown in the diagram, we have a distributed storage system managing the 2 storage nodes. And then on top of that, we have many types of cloud services. In this study, we focus on 3 of them. Our block storage service, our EBS, and then we have our NoSQL data service, our version of Dynamo, and then we have a big data analytics service. So part of the analysis investigation involves collecting the node device level error logs and all the information and feed them into the big data analysis and run analytical workload there. So this, our study covers about 500,000 SSDs used by these 3 services. These services are deployed in pretty much all regions of Alibaba Cloud, and usually more than 1 DCs per region. In total, we look at the SSD deployed in 7 data centers. These SSDs consist of 5 models from 3 different vendors, different capacity and lithography. They are all MLC SSDs, and at the time of investigation, most have been used for 2 to 3 years. The table on the right shows how each service uses SSD. Next, we'll define how we come up with a term called RASR, as reported as SSD-related failures. So our investigation methodology involves analyzing node, device, and repair logs, and smart data, and also conducting field studies inside the data center, and we do some experimentation as well. So across the 3 services, over a 3 years period, we collected about 150,000 failure events. So every node in our data center has the background monitoring daemon that monitors every component on that physical machine, mostly hardware related, but sometimes OS related as well. Every time he sees a problem, he reports that to a centralized service, and that problem gets tracked and eventually repaired. So across the 3 services, we collect 150,000 events. Most of the time, the monitoring daemon can tell what's a problem. And about 20% of the time, he cannot, and that's he marked them as unknown. He already ends up with whole node replacement. SSD-related failures accounts for about 6%. Those are the focus of our study. That's why we call them reported SSD-related. The 6% number is consistent with the fact that SSD is generally more reliable than hard drives and requires fewer node replacement. We further divide the SSD-related failures based on their symptoms, ranging from node unbootable, drive not found, to file system corruption, media error, which is basically read failures, and buffer I/O error, which correlates to write failures. Our on-site SREs has a fixed step of repairs. They're symptom-based. It range from simplest node reboot to the most expensive one, drive replacement. And then depends on which results repair step actually fix the failure, we give it root cause. For example, if the on-site SRE fixed the failure with cable replacement, after he tried node reboot and running file system checks, we think the root cause is a faulty cable. Next, we'll cover the lessons we learned from studying these SSD-related failures. The first one comes from hardware design and node placement within a rack. This is a puzzle we encountered at the beginning of the research. It's a once very common SSD model, and used in a very common service. But in one particular data center, it has more than double the media error rate than the same SSD used in the same service, but in different data centers. As I mentioned, this is media error, so those results will lead to replications at service layer and affect service performance and even availability. And those media errors usually end up with drive replacement, costing us money. So I'll skip the details about how we find the root cause, but the reason we think is passive heating. We define passive heating as an SSD that has been through relatively idle SSD has been through high ambient temperature from hot neighbors for extended period of time. Hot neighbors can be other hot SSD in the same node, or hot nodes next by, or hot nodes in the same rack but through some empty slots. In our log, we have seen SSDs rise up above the ambient temperature by up to 25 degrees C or higher. The paper has more details how each type of, in our experiment, each type of passive heating can heat up an idle SSD under our standard rack setup. The reason for why this one only happens in the one particular data center is that in all the other data centers, a service owns a whole rack. All the nodes in the rack belong to the same service. So they have similar workload and similar temperature, not much interference with each other. In this particular DC4, for some reason, nodes from 2 different services are mixed together, put into the same rack. Besides the block service, the other service is a heavy compute service. The service tries really hard to maximize CPU usage and drives the node temperature. And the OSSD storage node next to it suffers from passive heating, and it's been going on there for a long time until our study found out. Right. So here's another experiment where we increase the ambient temperature of an idle SSD from its default 25 degrees for extended period of time up to 128 hours. And then at the end of the test, we read the whole drive and look at its raw bit error rate. As you can see from the graph, the higher the temperature, the longer the period that the node is under that temperature, the higher its raw bit error rate. The temperature is controlled by running compute-heavy workload on the CPU. So this is our compute node with one data SSD. We keep it idle for extended period of time. We take a smart reading once every 15 seconds to make sure the temperature stays relatively within the narrow range. Passive heating is different from active heating, which comes from SSD's own internal activity. SSDs has their own internal temperature control. When it becomes too hot, the FTLs can throttle its activity, lower its throughput to lower its temperature. But under passive heating, there's not much thing the SSD can do. His FTL is basically idle, and the raw bit error rate accumulates, and eventually leads to media errors. So for solutions, besides not to keep a compute node next to an OSSD storage node, we have two suggestions. The first one is periodic scanning at the host level. We repeat the same experiment, heating the SSD to 55 degrees C. Instead, leave it there for 128 hours. Every 4 hours, read the whole drive. This take about like 15 minutes. And then at the end of 128 hours test period, we measure its raw bit error rate. It's only about 1% compared to the 57% without the scanning. Different type of this kind of approach is used one way or the other. However, it's probably not the optimal, as the drives are getting bigger. It takes longer to read the whole thing. And the read disturb from frequent scanning will have negative impact. So the other solution we suggest, which requires vendor support, is to move the scanning into the SSD itself. Since STL already knows its temperature, and he has read refresh capability, and also he knows the quality of NAND chips, so it seems much more appropriate for this kind of activity to be inside the FTL. So the second lesson is about software and system architecture. So we look at the three services with their SSD usage over a long period of time. We first look at their average usage. They all look normal, especially, for example, the block service and the NoSQL service. They have similar host read and host write hourly rate. However, if we look at the coefficient of variance, which is basically the standard deviation over the mean, we see a big difference between the block service and the other two. Both the big data and NoSQL is relatively nice, single digit. The block service are double digit, which means the SSDs under the block service has very diverse usage pattern. Here's one particular block service OSSD cluster, and this is the average over 3 months. On the x-axis is the hourly average host write rate. As you can see, on the y-axis is the normalized number of nodes at that write workload. As you can see, the usage ranges from less than 0.5 gigabytes an hour over 3 months period to about 10 gigabytes an hour over the 3 months. On the contrary, the SSD usage distribution for both the big data and NoSQL service is much narrower. Such diverse usage pattern can lead to uneven SSD wear leveling at the cluster level. That a subset of SSDs experience heavy usage, early wear out, and more errors later on, while the rest are barely used in the cluster. This will become an increasing problem as SSDs are getting bigger, but they come with lower DWPDs. The reason for the diverse usage is still caused by the design of our first generation block service architecture. The first generation block service takes a simple approach that directly maps a user level LBA to a triple replicated physical SSD LBA range, and use in-place update to serve users' write request. Both the mapping and the placement are relatively static. At the initial placement, the block service knows very little about the access pattern or how hot or cold the user's LBA range would be. So we directly expose the LBA of the physical SSD to the diverse access pattern of EBS users. The solution, well, this is our second generation EBS block service design, which uses a log structure approach. Instead of in-place update, user updates are written to a different drive, different location, most likely on a different drive in the same cluster. And the block service keeps track of where the data is and updates and the garbage collect data in the background. OSSD sees the pen loading traffic from the host. The new block service was GA'd about a year ago, and we observed its coefficient variance is about 5% instead of the 25% in the previous design. The new design obviously has a trade-off that now there are more writes to the SSD from the GC activity from the service layer. The third lesson comes from the administrative point of view. This is a rehash of the previous slide showing the under the drive failure case. A drive now found accounts to like more than 50% of the SSD failures. And this is all the steps, or the major steps that actually fix the problem. One thing worth noticing that is replacing cable accounts for more than replacing SSD. We want to look more into the cause of that. One particular type of smart data got our attention. It's called Ultra DMA CRC. It records the CRC, the data fails the CRC check after the SSD to host transmission, which will trigger automatic retry. Sometimes, most of the time, the retry succeeds, and then the error is considered benign, transient, ignore it. However, we see a strong correlation between the UCRC error code and the faulty cable root cause. I'll skip further since we're running out of time. So another lesson we learned is significant amount, 20% of the time, the failures is caused by human errors, caused by wrong slot. People stuck the system drive into data drive slots. And the solution we come out is called one interface, one purpose. We intentionally choose different interface, M.2 for system drive and SATA for the data drive. And for conclusions, so we look at about 10,000 SSD-related failures in our system over the 3 years. And we evaluate them from 3 angles, hardware, service design, and administrative point of view. And the conclusion is, so first one is passive heating in data center is real because SSDs is less temperature tolerant, and they consider hot tier, and they stay close to CPUs and other SSDs. The second, we should pay attention to wear leveling at the cluster level. Because otherwise it will cause uneven wear leveling among the SSD populations. The third one is, although bad drives gets most attention, faulty cable is more common than people think. So it's necessary to find good indicators for that problems. And that's all I have. Thank you, and happy to take questions.
Questions? Okay, I have a question from almost the very end. You mentioned that faulty cables are a big cause. Do cables actually go bad?
Yes, and there are two parts of it. One is the interface between the cable and SSD, and that can go bad. And in that case, if you're replacing cable, I mean, although you see the UCRC errors, but it may not be the cable's fault. It may be the connection between the cable and SSD. But more likely, it's the cables having problem.
Is this mechanical disturbance then that's causing the cables to fail?
I don't know the exact details, but we do see a significant number of cable having to be replaced.
Russ Blaine, Apple. I'm just wondering if those errors during elevated temperature levels are transient or if they're permanent somehow.
So they end up as media. So what we see is media errors. It's double the default case. So the fix for those things is usually drive replacement. It could be that maybe the FTL is smart enough to skip those bad NAND chips. The drives becomes usable again, but it just lower the quality of the drive.
Okay, one more question.
Hello, this is Liang from East China Normal University. My question is, what kind of error correction scheme you used for the SSD array?
Inside the SSD or at the service level?
In both.
On the host level. Okay, so this is a typical distributed system. We have either erasure coding or triple applications at the service level. Yeah.
So what is inside the controller?
Well, I mean, it's kind of a vendor secret. We don't know much about that.
Can I ask one more?
Yeah.
As I know, in Alibaba, they use open channel SSD. So
No, those are all commercials. I mean, those the open channels are still under development. This study was like conducted 2 years ago. I think all SSD at that time were SATA commercial SSDs.
Okay, thank you.
Yeah.
All right, let's thank the speaker.